Fundamentals of Multisensor Metrology, presented by Tom Groff, Optical Gauging Products, Division of Quality Vision International. Today's manufacturers are faced with the challenge of measuring many different and complex features on component parts they make. Conventional methods of measurement do not have the capability or flexibility to meet these needs. Complicated dimensions and form cannot be measured with simple hand tools. Take this femoral implant, for example. It is not easily measured using a caliper. To successfully measure this part's complex details, we need a measurement system with advanced sensors and technology. Think about how you interact with a manufactured part. You touch, see, and feel using sensors. Now think about how an automatic measuring machine must interact with a part. It's the same. The measuring machine uses a combination of vision and touch sensors to evaluate a part. Multi-sensor systems allow you to use best practices to measure every feature of a part. This simple example illustrates the need for multi-sensor technology. Surface A, chamfer B, counterbore C, sidewall D, and bottom surface E each have different measurement needs. By selecting the best available sensor for the measurement at hand, you can measure faster and with a lower uncertainty than using a single sensor that may not be optimal. No compromises, better accuracy, maximize capability. The first sensor that we generally employ is vision. For a measuring machine to see, we have to give it eyes. That means using optics to image a part so we can examine it. Simple vision systems, such as microscopes, are good for visual inspections. A microscope allows us to magnify and see the detail more closely to spot a defect. In order to perform measurements, we have to go a step further and digitize the image so it can be analyzed by software. For that, we use a video camera. There are several techniques for acquiring and measuring video images. Here, we see an example of basic edge detection. In this scene, there is a lot of image data, most of it either all light or dark. What we're interested in is the area of transition between light and dark, the edge of the part. To speed up measurement, we can tell the measuring system where to look for an edge. The green box shows the search area we've used to tell the measuring system where to look for the part edge. In this case, we see the found edge, indicated by the green plus signs. We also see there is a defect of some sort, most likely dust or a burr, which can probably be easily removed and is therefore not important to the measurement. Image analysis tools enable us to filter out the dust and burrs so our measurement is not impacted. The settings used to determine what is a defect must be flexible so we can adjust them to suit the conditions of our part. In this scene, we're using what's known as a blob analysis tool. This type of tool searches for all features in the image that meet specified characteristics of size or intensity. Blob tools are really useful when you know there will be features of interest in a scene, but you are not certain where they will be or how many to expect. Using blob, we can find and measure all the qualifying features at once and segregate them according to size. Once we know the location of each feature in the scene, we can go back and perform a more detailed measurement. In this example, we use the blob tool to locate the center of the 4 countersunk pockets. Then we use those known locations to place edge finders on all the sides of the pockets to measure them. In this example, we have a focusing tool which enables us to see a cross-section of a part without touching it. This part is a die made to cut decorative paper. The multicolored plot shows the measured image of the die. In this scene, we see a frequent problem in optical measurement. The surface of this metal part is very shiny, so shiny that all the light reflects off it and we can't focus it sharply. A similar problem occurs when we try to focus on translucent materials. The light passes through the surface, so we can't see it clearly. In order to focus on areas like these that have no natural contrast, we can project an image of artificial contrast onto the surface to give it the appearance of texture. The checkerboard grid pattern is focused exactly at the focal length of the optics. The grid appears sharply focused when the part surface is in focus. What happens when the thing we want to measure is too big to see in one snapshot? One way to measure large features is by taking lots of snapshots and then combining them into one large image. In this example, we stitched 12 snapshots into one image to allow simultaneous measurement of the leads on this chip carrier. Focusing on the top of the part with an autofocus tool, it is finding the Z surface and setting that as a datum. Here we are seeing a routine with both focus measurements and size measurements being performed automatically. This system is able to make multiple video or focus measurements simultaneously within its FOV, known as parallel processing. Here we are using edge detection to identify the perimeter points, and then we use parallel video processing. So all of those edges are getting measured at once by taking a snapshot that gathers thousands of data points at a time. The results are 792 features measured in 9 seconds. Video is great at high throughput for very quick, very accurate measurements. In this example, we need to measure some very small parts. So small they're almost impossible to hold in a fixture. This is the sort of situation where video measurement is ideal. It would be nearly impossible to measure these tiny parts using a hand tool. To use any kind of tactile probe, we'd need to have fixturing to hold the parts steady for measurement. Using video measurement, fixturing is not needed since we are not physically touching the part as other sensors would. Here, we place a random batch of parts on the measuring surface and use a routine to map the entire measuring range. We then form a big picture of the stitched fields and identify where the parts are, what orientation they are in, and then we are able to apply the detailed measurement routine, using video or multiple sensors such as laser or touch probe to complete the detailed measurements. Some kind of measurements simply can't be done using visual methods alone. For example, using optics alone, the side of the part cannot be measured. To measure down the outside or an internal feature, a touch probe is needed to reach in and measure where the optics can't see. This particular example uses a CAD model to program the part. We have identified the clearance zone around the part so the machine can easily maneuver the touch probe around the part without crashing. With the clearance zone in place, we can proceed to measure by acquiring points at various locations on the part and construct them into desired features. The next sensor we are going to talk about is tactile scanning. Tactile scanning is highly accurate and reasonably fast for acquiring individual data points. Measuring with a scanning probe combines high precision in probe path and the machine servos to keep the probe in constant deflection while moving around the part to acquire thousands of data points. The probe path can be programmed in CAD as shown in the upper right-hand window. A probe path can also be programmed to scan an unknown contour. To do this, we tell it the start point and the end point and let the probe find everything in between. The benefit of this technique is that we acquire a lot of points during the scan, making for a highly precise measurement. Tactile and scanning probes work well for many measurements, but there is a practical limit to the size that can be probed. For these very small features, we need a micro-sized probe with micro-probing force. We call this a feather probe. Instead of triggering a measurement when the probe deflects, the feather probe triggers by sensing a change in resonance when the probe comes into contact with a surface. The feather probe is constantly resonating at a high frequency, and as soon as it gets close to a part or actually touches it, the frequency changes. This technology is ideal for measuring parts that are flexible and can't be accurately measured using conventional probing force. The feather probe shown in this video requires only 5 milligrams of force to trigger. So little, it can probe a feather without deflecting it, or probe the surface of water without creating a wake. When a feather probe is deployed on a system with a video sensor, we can combine the two, using the video to guide the probe into the feature of interest without crashing. When measuring tiny little features, that becomes very important. Another unique application of a touch probe is the optical interposer. In this image, we see a tactile probe deployed underneath the optics so that we are imaging the tip of the probe, shown here as a little dark circle. We can then move the probe into contact with the side of a feature, such as this hole, and then measure the probe location using video. Subtracting the probe diameter from each measurement point allows us to make optical measurements deep inside the hole in locations that optics alone could not reach. This technique is especially useful when measuring really small features that are obscured, such as the raceway in this bearing assembly. Using our optics alone, we cannot see the raceway, but by placing the interposer in the groove, we can clearly image the groove center location and measure it. The interposer uses the high-speed accuracy video combined with the touch probe's ability to reach into places that video can't easily see, such as a bearing way deep inside a bore. Lasers are another important center in the multi-sensor arsenal. Lasers are high-speed and non-contact devices, great for scanning surfaces, and very accurate for making height or depth measurements. In this example, we see the most common type of laser measurement tool, the triangulation laser. QVI offers a number of different lasers of this type on our multi-sensor systems. The diode emits the laser beam, which reflects off the part's surface and is collected through optics and delivered to a detector array. This type of laser works well as long as the laser can reach the surface and has an unobstructed return angle back to the detector. Here's what happens when you run a laser scan. Shown here is the laser scanning over a surface, and it is detected up in this array up here. Once the detector sees the spot, it is able to determine the height of the surface. Conventional lasers work well in many situations, but there are some practical limitations on them. When surfaces are both textured and very shiny, the laser light is scattered when it reflects off the surface, so that less of the light returns to the detector. This weak signal can contribute to data losses and reduced accuracy. Measuring inside a hole or cavity can also be limited. If the opening is too narrow, the laser's return path may be blocked. Conventional lasers have a preset capture range and working distance, with the working distance typically being relatively short. Thus, it is not easy to measure deep inside a part using a triangulation laser. For these situations, other types of laser sensors are needed. Our patented Telestar Plus is designed to handle these types of challenging situations. The Telestar Plus combines a visible light laser with a sub-lambda interferometer, in other words, an invisible light source. It offers a very long working distance, near zero return angle, and is designed to work well on specular surfaces that scatter conventional laser light. The interferometer has a built-in reference so that it continually compares the distance between the focal plane and the part's surface to the reference distance. This allows it to perform very high accuracy measurements under a wide range of conditions. The Telestar Plus is known as the super laser. It is equally accurate on all types of surfaces and requires a very shallow return angle so that it can penetrate into deep, narrow spaces that an ordinary laser couldn't reach. Let's look more closely at the principles behind interferometry. A light source gets projected down onto the part, and then it is received back up as two opposite paths. Depending on the timing between when those signals are received, the detector can tell how far away it is from the part. Shown here, we are scanning a part. As the part moves further away, you see the arrows coming back to the detector at different times. Sometimes the green arrow is first, and sometimes the red arrow is first. One more type of laser sensor, although not technically a laser, is the chromatic sensor. A laser light source has a single wavelength, 760 nanometers for a conventional laser. The chromatic sensor uses a broad spectrum light source, true white light, which is composed of many individual wavelengths. The chromatic sensor intentionally separates these wavelengths into individual colors. Because only one color is in perfect focus at a given time, it is possible to measure with much higher resolution than with ordinary white light. Unlike a conventional laser, the chromatic sensor can be used to measure translucent materials, such as plastic or glass, that a laser would pass through without reflecting. Here is an example of measuring a lens. The result is a plot like this with nanometers of accuracy. This type of sensor has a very high resolution and nanometer accuracy. Let's look at some real-world uses of multisensor measurements in manufacturing. Here we are measuring the size and orientation of orifices in a fuel injector nozzle. Because these holes are very, very small, we are using a combination of optics, laser, and a feather probe to measure them. First, we scan over the part which has been fixed on a rotary indexer at an angle to align the part axis. Then we scan over with the laser to identify the characteristics of the tip. After that, we can use a tiny feather probe with a 120 micron stylus to measure the diameter of the holes and their orientation relative to the part axis. Another multisensing example. Here we are using a scanning probe to measure the large features and some internal features. We do a very quick laser scan on the top of the part to acquire thousands of data points to determine flatness or curves. Then we go in with video and measure some surface features and small features. With multisensor technology, a single piece of equipment takes the place of several different systems, reducing capital costs, floor space, training, and staff. And a single multisensor system reduces overall measurement uncertainty, leaving you with more of the error budget for the manufacturing process. Multisensor measurement also saves time. Using the same equipment to measure parts at each stage in the manufacturing process means there is no need to have multiple setups for different kinds of parts or different kinds of features on a single part.